Hello class, today we are going to go one step further and have a heater under our heatsink, because if you remember from the previous weeks, our heatsink has a higher temperature, for example 100 or 200 degree, and we put it outside in a fluid, for example air, at lower temperature, and we waited for that hot heatsink or any surface to cool down using by natural convection. This time I'm going to add a heater under our heatsink. So basically adding heat flux boundary condition to the bottom of the heatsink, and see what is going to happen instead of having initial temperature, but still it is going to be a natural convection cooling. Okay, let's start with Fluent, and I'm going to use the previous geometry we had, which is this one, and I'm going to have a coarse mesh because we're not looking for accuracy right now, just learning the procedure. Because I already draw that geometry in SolidWorks, usually takes a bit time for the Fluent or ANSYS to import that file. Okay, mesh is here. Let's go and generate mesh. It's nice because it's a uniform mesh, and you know from other previous subjects, uniform mesh is much better than non-uniform mesh, because we want to have a smaller mesh. That is why we go for the non-uniform mesh, and which is going to decrease our a little bit accuracy. Okay, this is really coarse. Let me make the size function as a uniform, and fine. A little bit better than the previous one, but still we could have a finer mesh close to the surface, which we have a higher temperature gradient here. But yeah, we're not looking for accuracy right now. Geometry part 1 is a fluid. Let me rename it. This is going to be fluid or air. This one is going to be our heatsink. I could change the material here for Fluent later is going to understand this. Solid, fluid here, or you could go and later change it in zones when we open the Fluent. Okay, let's put the names there. As you remember from the previous homework, we decided to have these two sides as a wall. So where is name selection? So walls, and air is going to come from left and right side. So let's name it inlet, and it's going out from top because we have natural convection on air. When it's heat up, outlet, it's going to go and move upward. Okay, this time I'm going to have heat flux from the bottom. I didn't draw any layer here as a representative of a heater. I could have that, but I didn't see any reason, so I'm going to put boundary condition heat flux here. So later, because I want to find this surface, I'm going to name it, for example, hot surface, and we're done. Let's close this, update mesh. Because we need to have this red green check there currently. Okay, we got it. Open setup, double precision, parallel, use 4 cores of my computer if you need. And okay, Fluent is ready, everything is here. I would like to have a transient simulation, pressure based, absolute values, gravity, because we have natural convection and gravity is very important, because when air around this heatsink gets hotter, it gets lighter, and gravity causes cold air to come down and the hot air go upwards. So negative 9.81 for y direction, as you can see here, y direction. We are happy with this one. Let's open models. I have temperature, so I need to turn on energy. The other one, materials, natural convection. So let's change air to incompressible ideal gas. Click change and create, close it, and still I'm going to use aluminum as a solid. If you want to change it, you can open Fluent database and here select solid and check other materials, gold, copper, everything you want. Okay, let's close the material, cell zones. This is the fluid one, it's automatically selected. HC, it's solid, again automatically selected, because during my defining mesh I already told ANSYS this is going to be a solid and F is going to be for fluid. Let's turn on business approximation and initial variable density parameter. We need to specify it, otherwise we're not going to have natural convection, so I'm specifying it. Okay, let's open boundary conditions. Inlet supposed to be a pressure inlet. Basically, I'm telling ANSYS for inlet left side and right walls, we are going to have how I can say no velocity income we are having, but it's going to just create a pressure balance between these areas when we have inlet, pressure inlet. For outlet, again, no velocity is specified, just pressure outlet automatically is selected, and depends on the flow, it is going to adjust this pressure at our outlet. Let me check again, operating condition, it is turned on, this density parameter. What else? Oh, I need to specify hot surface. Okay, so because I want to have a heater at the bottom, I'm going to have a heat flux, and let's say 1000 watt per meter square is going to be our heat flux. Done with it. Interface, make sure you couple between solid and liquid, fluid. Here it's air. Edit. This is the contact region for the solid part and fluid part, and you need to check coupled wall to make sure the mathematical equations are ready for us. Okay, no problem with this one. I don't want to change. This is reference values. I'm okay with that one. Method, because we have solid and liquid, you need to change pressure velocity coupling scheme to coupled. And for pressure, as we said, you can select body force or presto. I'm using body force. The others are second order. you can even increase the accuracy of transient formula to second order, but for now it's okay. For the controls, these are the relaxation factors. Basically, relaxation factors are the numbers between 0 and 1. When you solve CFD equations, for example this case, each time when you're updating velocity, temperature, or anything else, using these relaxation factors, you don't want to change those parameters very fast. For example, from 20 degree to 25. You want to have more calculations, but less changing in your temperature. So you, for example, change these relaxation factors to decrease the amount of change we have, which makes our calculation much more stable. Yes, let's make sure we are saving some data, because this is a transient simulation, so you need to specify what you want to save. So let's change the file type to CFD post compatible, which is understandable for Fluent. Later we can read it, select all the surfaces, so all the information for those surfaces. I would like pressure, where is all the velocity information, and also temperature. Yeah, it's enough. Every 10, for example, time step is good, and you need to specify where do you want to save those data. I'm going to save in my desktop, test, new folder number 2, and as I said earlier, you need to delete this address and keep just the name here. Otherwise, this address is going to be your saving address, which you don't want. This is the default address. So save it. Now you can see this is my desktop, test natural, new folder number 2, and it's going to be saved every 10 time step. This is a saving frequency. Okay, I made sure that I'm saving some data. For initialization, this time I'm going to use hybrid initialization. Wait for it to show. Okay, hybrid initialization is done. Now let's go and run it. The number of time steps, let's go with 1000. You can click this check case to see what type of comment it's going to have, and Fluent recommends you to improve the mesh. Yeah, but we don't care, and we're happy with this mesh size, and that's it. And for the time step, this is a bit advanced. Maybe later in next weeks I explain how you can decide what size of time steps you can select. We call it CFL number. Some of you may know, but later I will discuss about that. This is, I'm going to select 1 second. This is really large number, but yeah, I would like to have a result much faster, and the accuracy is not our priority here. Okay, let's start calculation. This is a residual graph. Usually we expect everything to go under 10 power minus 3. 10 power minus 3 is the basically default number, which is like a base number. For the fluid analysis CFD works, we usually decide to have a 10 power minus 6 as a residual criteria, and basically we force calculation to have a residual less than 10 power minus 6. Here it's less than 10 power minus 4, but it's okay. Just remember, if you want to have a better result and much more accurate, this residual number should be decreased to at least less than 10 power minus 6. Let me check if we are saving some data. As you can see, this is the folder I decided for the Fluent to save our data every 10 time step. First one is 10, the second one is 20, so every 10 time steps you are going to see these data are being saved. Let me pause the simulation, this recording, and I'm going to come back after having enough data. Okay, I stopped the simulation. Let's check some of the results. I'm dragging some results here. Open the results. And because this is a new result, it's not connected to the previous simulation, I need to manually import the result. It's going to be on desktop here, new folder number 2, and you need to go for the latest one and open it. Okay, the results are here. You can see the geometry. Let me draw a plan. This plan is going to be, for example, here, almost at the center. And let's check the temperature counter. It must be our plan we just defined, and I'm looking for temperature. The number of counters, let's go with 50, and this is our counter perpendicular to the XY axis. You can see the highest temperature is about 50 degree here, and room temperature is 26, which was default. I could change that. If you want to change the room temperature, you could where is it? Zone condition. Let me check boundaries. Inlet, outlet. Yeah, where is inlet? Thermal, this is 300. I could change it to any temperature I want. Also for outlet, I could change temperature here. So this 300 degree, which is 26 something, as you can see 26.8. This is the room temperature, and instead of specifying an initial temperature which we had for previous homework, this time we have heat flux coming from the button. Let me check what's happening at the initial, like the first 10 seconds. At first 10 seconds, nothing happens. 26.8 everywhere. And let's see as time passes how temperature profile changes. See, temperature at the button increases, and this fin works like a pump. As you can see, it draws heat from the button to this surface. Now you have much more surface here to convect heat to the air. See, you can see kind of a wave from here, from base, sucking in the fin. and it gets hotter as time passes because our base is getting hotter, and basically our heater is at the bottom. We turn on heater, the temperature rises, and fin tries to take the temperature far from the base, and we have a convective heat transfer here. Okay, let's this time show you what is isosurface. Let me turn off this one, contour and plane. Over location, we have another option, which is isosurface. I'm looking for temperature. For example, 35 degree. Everywhere with 35 degree surface is going to be part of that surface. Let's click it. Now you can see this is the isosurface for 35 degree. If I increase temperature, this surface is supposed to get closer to our fin. Let me increase, for example, 45 degree. Yeah, it gets much more closer to the fin, even more. Okay, and if I decrease it, it's going to be far from it.